our next speaker, Paco Nathan, board member and advisor at Argilla. Paco has been collaborating on European AI initiatives, has been deep into the NLP and data science space, working with companies like BASF and Siemens from the industrial sector. So please join me in welcoming Paco.
Thank you very much. I'm really grateful to be here today. And I think especially this conference is so incredibly valuable based on the people who are gathered and the conversations. Earlier, Dr. Mitra, years ago I studied circulence, but I saw your mention of approximated block circulence. I think that's the first time I've ever actually seen an application, so I'm grateful. And also, this is a longer talk, which is condensed, but fortunately, Christopher and Sudhir and Waleed actually covered probably about half the talk already. So I'm going to give a condensed version, but hopefully I have some examples, in fact, some sample code. Also a lot of primary resources and links, tutorials, et cetera, that might be helpful for you. So you can get the slides here off this QR code, and it's all online. My name is Paco Nathan. I lead a team called Darwin. We do work AI applications in manufacturing. Last year I gave a talk here with my colleague Jürgen Müller from BASF. Certainly I don't speak for BASF, but we do a lot of work with them. I've also, as mentioned in the program, I'm involved with a company called Argilla. We've been around for 6 years. I've been advising the team since they started. We were actually spacey committers is kind of how we met. And in 2017, the company got together to do work on large language models in enterprise use cases. And for the first few years, a lot of people would hear what we were doing and they would say, well, that kind of sounds like a niche. I don't know, commercial applications of language models. I don't know if that's really going to go anywhere, but it's been an interesting 6 years. I'll show some parts of both those companies we work together and have some customers in common. I'll show some of that here. So the talk I have is really about this space of graphs meeting language models, how that applies in AI applications. And earlier talks today, like I mentioned, have covered a lot of this. It's interesting because if you look over the past few years, going back to like Michael Bronstein's geometric deep learning and all that came out of it, PyTorch geometric, et cetera. But there's been a lot of work on graph machine learning. And really, if you roll the clock back a couple of years, if you wanted to get a paper published in this space, you probably needed to mention GNNs. That kind of peaked in about 2022. And large language models, there was a reference to it in a Google paper, I think from 2008, but this really started coming out in 2017. So attention is all you need, of course, is the real foundational paper. And you can kind of see the trend lines of where these have popped up. We're looking at the idea of where graph machine learning and large language models fit together. And so for that, let me see, I'll try to get out of the way. The idea is, as some other speakers have talked about, you can use natural language to construct graphs from sources. And it's really difficult when you get into unstructured kinds of data sources. If you're working in manufacturing, you have hundreds of millions of PDF documents. And some of these describe patent applications from entities which are probably your competitors, you don't actually know. Some of these describe environmental impact reports, also from your competitors. Some of these are shipping manifests. Your sales data is in bill of materials, which are graphs. There's scientific papers in material science, et cetera. So you end up with hundreds of millions of PDF documents. You have to pull data out from these unstructured sources. And when you get that data, by definition, it's linked data. These are graphs. Obviously, your vendor network is a graph. That feeds into your sales and your production data. That feeds into your compliance norms and patent applications, et cetera. So we're very interested in how we can leverage this kind of technology to be able to build graphs, but then also on the other side, how can we leverage this kind of technology for the end applications? And as some have mentioned before, one of the really good ways of doing this is question answering systems, basically querying your data, querying your systems, where graph data really becomes your ground truth for what you have. Now, the thing that I want to represent in my talk is that over the past 5 years, there's been a real flurry of a lot of open source coming out. And so I've put up kind of a NASCAR slide on the bottom there, but these are some of the projects that we work with, some of the open source projects and libraries that we've found very useful in this space of this intersection between GraphML and large language models. And there's more. This is really all I could fit on the slide. A lot of this, of course, is available in Python, or under the hood it's Python, C++, or Rust, usually. The problem, though, is that even though there's been a flurry of papers coming out and so many open source projects, anybody in the world can go out and publish a repo on GitHub. It doesn't necessarily mean that it's good code. And so it's actually kind of a software engineering challenge to look at the new open source that's coming out of research that's associated with the papers that are coming out. It's really challenging to be able to evaluate all these libraries and figure out what works and what doesn't work. And in the context of a small vendor working in AI, working with a very large manufacturer, this is actually some of the more valuable things that we can provide them, is really finding out what works. How can we provide building blocks for their projects internally? I also want to point out there are some labs that we're tracking. Of course, there are many others, but these are some of the labs where we've been working with people with their open source projects. Maciej Besta, especially at ETH Zurich, and Semi at Waterloo, Oscar at UPM Madrid, and others. And I've been implementing some of Rada Mihasia's theoretical work in open source for many years. And also in this space about where do knowledge graphs, where does graph machine learning intersect with large language models, there have been some very good tutorials. I definitely wanted to put these front and center. Jerry Liu has a great set of talks, but also on Llama Index, there's some wonderful tutorials with a lot of code. If you want to go in and start looking at how to use, for instance, a knowledge graph as your grounding for retrieval augmented generation. And there's some others. Tony Seal from UBS. Shirui Pan's paper is more of a survey paper, but that's where that graphic comes from. So there's a lot of good information out there. And I have kind of an opinionated view of some of this because we work more on the open source side. So the very large technology firms, of course, have been very vocal about having extremely large models. I tend to favor more of what's going on with smaller specialized models, as Christopher was mentioning earlier. I think that the open source AI model ecosystem is very rich. In September it was 3,040. Now in October it's 350,000 models in Hugging Face. So at Argilla we work closely with Hugging Face, and we're up in Hugging Face spaces. And I really appreciate all that Hugging Face does as a catalyst of building up this open source ecosystem. Okay, and so this is just kind of a hypothetical view of what might be going on in a given enterprise business use case. And the idea is you've got some enterprise data sources, you've got your graph, you're going to be working on enhancing the data quality of your graph, and then you're going to be using some combination of different types of machine learning toward your business use cases. Now, I mentioned GNNs. I'm just using that as a shortcut for graph ML in general. There's actually not a lot of use cases of GNNs in industry yet, but I think that's changing. And so I want to show an example here of something that we see in manufacturing a lot. The idea of, essentially your sales data is bill of materials. And so you have a BOM to describe whatever you're providing to a customer. It's a little hard to see, but if you get the slides, you can see it. Here, instead of showing anything confidential, I live in Sonoma Coast, a little bit north of here. It's wine country. And so this is a process for making a certain kind of wine. And actually, I have all the data for all the different parts, but I kept some of it confidential. But this is typical. What you would see in manufacturing, of course, is a graph out of a BOM. Now, an interesting thing about this is that inside of this graph here that I showed about winemaking, there's a kind of object that shows up multiple times. Actually, I think it's like 5 different instances in this one recipe. And so this is what we would call a motif, at least in GraphML. We talk about motifs as being a kind of pattern in a graph, a small subgraph. The thing about motifs is if you're familiar with data warehousing, data lakes, motifs are essentially data objects in knowledge graphs. So if you can identify some areas of your graph that have common geometries, then you can start to use those as objects, as like first-class citizens. You can think of this as a way of transforming your graph, maybe even think about it as a way of graph compression. Because once you do start to collapse down the motifs, you can get a lot more predictive power in your machine learning. But okay, so if I take this process where I've got maybe some grape juice or apple juice, I've got a yeast, I've got a nutrient, then I go through one process of fermentation, a process of racking, I have a byproduct of compost, I get an intermediate product. And here I'm pulling in data about suppliers, process, byproducts, inventory, et cetera. One of the things that we can do with just a few lines of code, here I'm using an open source library out of Johns Hopkins called .motif. And just a few lines of code in Python. We have an executor that's looking for graph isomorphisms for that motif, which I've labeled and put some properties there off the graph. And now I can go through and search, and I can do my machine learning based on that. Now, I mentioned before there are tutorials about this intersection of knowledge graphs and what's going on in large language models. Very interesting, but a lot of these tend to go toward we are going to get some giant model that will take in a bunch of raw data and spit out a graph. I like to look at that much more deconstructed. I like to look at the different parts and do some more careful task analysis within that, and then understand in a very narrow focus, how do we augment the individual tasks? And so ultimately with the graph, what we're trying to do is build up our nodes and build up our edges. And there's really great work that's been augmented lately in named entity recognition, also in relation extraction, and I'll show a couple cases of those. But overall, this is kind of the approach that we're using on some applications. We start out with a bunch of documents, like I mentioned, a bunch of PDF. We run through, do some parsing. We build a kind of hypothesis graph just for a given document. But then we can do other manipulations on it, leverage the machine learning, leverage domain expertise, and start to come out with parts that we can go back and put into our knowledge graph, augmenting it, and having that feed into the end-use applications. Breaking this down step by step, you start out with some raw text, and maybe use Spacey. I really like using that, and our team does a lot. When you do this level of natural language analysis, you end up with segmented documents that get segmented into paragraphs, then into sentences, then into tokens, and then more importantly, going beyond a token, you can start to annotate and add part of speech, lemmatization, etc. Once you have that kind of annotated token out of your stream of your documents, there are graph algorithms that can be used. There's a family I've been working with for about 16 years. It's called text graph, and Radha Mahasya started this out in 2004. But the idea is from a raw text based off of co-occurrence using skipgrams, I can build up a graph, sort of a hypothetical graph out of that document based off of the products that I get out of Spacey and other kinds of models. And so for instance, I can go through and I can look at a given text. Here's a text that says Cleopatra the Seventh, also known as Cleopatra the Great, last active ruler of Ptolemaic Kingdom of Egypt, etc. I can take some raw text and having run it through natural language processing in Spacey, and then doing an additional step where I've augmented the named entity recognition with an LLM, I can take and start to pull out very high quality annotation of what the different parts are here, the different entities that are being extracted. And what's interesting there is, actually this is based off of a colleague's thesis recently called Span Marker by Tom Arson. What this means is that out of the raw text, I can pull out essentially the noun phrases. And for each one of those, I can start to annotate and say, well, I think this is a person or a place or a thing or a city or a historical period or an ethnicity, something. And what that means in a graph context is that thinking about semantic graphs, I can create a baseline that says that any entity, any node, I have a baseline for marking it up. I can say it's an owl thing. That's like the most general way to mark up something in a knowledge graph. But as I get more information, I can start to constrain that and go from something very general to something more specific. So I would call Cleopatra a person, but she's also a historical figure. And I can go into a lot more detail about Cleopatra by linking out to other resources. Similarly, for edges in a graph, I can use something called relation extraction. There's a really great work that's been done out of Tsinghua, if I'm pronouncing correctly, a university in China. Great set of suite of open source projects. But what I can do there is take a text, and I can take a couple of the entities that I've recognized previously, and within the context of where they're occurring in text, I can use an LLM to come out and say, what's the relationship between these two entities? Now, the interesting thing is with knowledge graphs, if you are working with controlled vocabularies, which is very common in industry, then I can start to map from what these LLMs are producing into specific parts of the controlled vocabularies. Again, moving from general to more specific. And a third thing that we can do by virtue of the text graph family of algorithms is we can take and sample from the knowledge graph that we're collecting. We can sample for the analysis that we're doing of a given document. And so this is based off of essentially a random walk, a semantic field random walk, but it's sort of like the knowledge graph analog of doing a nearest neighbor search in a vector database. So this is sort of an alternative, a little bit richer than doing nearest neighbor search. And at the end of the day, what this means is I can have my graph ML algorithms produce better rankings for the entities and relations that are being produced. That gives me a gradient. And a gradient then off of those annotations means that I could really build a recommender system. So I can have experts brought into the loop. For instance, here's a couple of Wikipedia pages and a fiction short story about Werner Herzog. We just ran it through and we came out with this graph that was produced mostly automatically. So the idea then is that we're using the graph as our ground truth, our data. And we want to enhance the data set quality. We want to do that in an iterative way, bringing in the experts, bringing in whatever we can refine out of machine learning. There's a lot of ways to do this. There are ways to filter. I wrote, like our company has an open source project for disparity filters if you're working off of a multi-scale backbone. There are tools like Shackle and SCAS that are very interesting for constraining domain and range. GraphML can be doing link prediction to infer missing edges. There's a wealth of work going on in statistical relational learning now. Probabilistic soft logic is one way of essentially providing probabilistic rule sets to graph relations. And at the end of the day, this is all about ways of being able to use the products from machine learning along with your experts to enhance your data quality and treating a graph as your data set. And so this is where I'll mention about Argilla. Essentially what we're trying to do is we start out with raw documents and we have parsed entities and relations. They're very general and they're very uncertain at first when they're unstructured. But as we apply these methods, we're moving from general to specific. We're also moving from uncertain to more confident. So by increasing those two, iterating to increase those two dimensions, we get improved data set quality. And just as a kind of view of what we're doing at Argilla, we've really focused more on enhancing data set quality and bringing in your domain experts at different points. And also being able to manage those teams, like having RBOC to describe how do you understand hierarchies of people who are domain experts who are giving you feedback, how do you use weak supervision to do tie breaking, things like this. And I really want to call out, there's been a lot of AI hype in the media, and a lot of talk about fully automating these processes. But yet when you look at really recent, this is from this year from Dimitrios Brinkman, where they did a survey of LLMs in production, 60% of the labeling is human-based, just to kind of give us some more fact. And so once we have, I'm going to scoot through this just in the interest of time. Once we have our graph, we can start to go into use cases. This is one I'll call out that's really interesting. It's called LPG2VEC. It's from CH Besta at UTH Zurich. We've been working with that code. But overall, once we get a graph that we can use this in a number of ways. When you have a data set, I can't underscore how important it is to work on the quality of your data set. You may be training models based off your data, if you have enough. You may be fine-tuning a pre-trained model with your data. Most certainly, you're going to be evaluating whatever models you're using with your data. It may be that you use few-shot. It may be that you use RAG to mitigate hallucinations. But those are already 5 different use cases for your data sets and really underscores the quality of your data sets. So I see that as being very key. I'll scoot through here a bit. One thing I do want to mention, though, as far as like an end use case, how many people here have ever seen chain of thought prompting for prompt engineering? Some people? Okay, so there was maybe 10% people there. There was an iteration of this from Princeton, Tree of Thoughts, to kind of make it more robust. And then out of ETH Zurich, one of the recent things is called Graph of Thoughts. And it's really interesting. It's kind of an operations research approach because they're really looking at cost models for how do they construct a graph to solve for a plan, for a complex strategy, using LLMs. And so the idea here is we get this kind of feedback loop closure where we're using a graph to ground what we're doing, but the LLMs are also producing graphs as the output, the strategy. So you could be augmenting your graph that way. And just in the time remaining, I want to talk about some of the risks that we've seen. It's actually some of our history is coming back to haunt us. When you look at the hype that's out in the news, there's a lot of noise. But actually, this is a really interesting survey recently. When you look at the academic papers that are coming out in this area, and there's only a subset of them that actually publish code. But when you look at the code that is being produced, and I've seen this so many times, our team actually works on this so much, the code that's being produced, you're going to have problems installing it. You're going to have problems getting it to run without exceptions. At the end of the day, when it comes down to actually being able to replicate the results that were published in the paper, the number there is 3%. That's the success rate. So even though there's a lot of research coming out and a lot of open source code to support that, it's very, very low quantities that are actually useful for some kind of production use case in industry. And on the flip side, we still have similar risks over in enterprise. We have a lot of places that just really aren't ready on their data. And it's very difficult it's like pulling teeth to get the proper data that you need out of corporate sources. All the way down to, how many people are really doing this in production? And this goes back to a series of surveys and analysis reports that Ben Lorica and I did a few years ago. Well, actually, let me scoot forward here. Showing that this is kind of a survival analysis, but what are the things that are holding up enterprise from using AI applications? And what we found, a lot of it was really at the top where the executives just didn't understand, or maybe they just couldn't get the right product managers in place. But then you also get a lot of companies that are suffering from data quality or lack of data, really trying to understand the risks. And then finally, you get down to the bottom cohort. These are the people making money, and they're worried about efficiency and tuning hyperparameters. This is from 2019, but it still holds today. This is a lot of the risk on the enterprise side of using these kind of applications. And the biggest takeaway, I only have a few minutes left. The biggest takeaway is really this. This is kind of a summary. We had a conference a couple weeks ago. Ben also was chair for that, called the AI conference. And it sold out really quickly. It was really packed, great information. My top 3 takeaways are this. Number 1, you want to prioritize curating the quality of your data sets. Number 2, you want to do very narrow task analysis. What is it you're trying to improve? Understand the tasks in very fine-grained detail, and then pick particular ones and augment those. Don't think about automating them initially. And then number 3, you're going to be using multiple models. You're going to be using probably more smaller models that are purpose-built for particular kinds of uses. And frankly, you know, what we're hearing from the inference side of running these kinds of models in production, they're probably not going to be CPU bound, they're probably going to be IO bound. You're probably going to be doing a lot of work with concurrency to avoid starvation in these models, which, you know, kind of pulls the rug out from underneath a lot of what's going on in the media about running some ginormous, super intelligent model in the cloud. No, you're probably going to be running it on edge hardware, and it's going to be IO bound. I'm going to scoot through. I thought this was really great from Niraj Weissblatt, that if you look at the people who are pushing AI panic, they're all men. So, you know, as a conditional probability, if women are up talking about AI, listen. If men are up talking about AI, yeah, you know, take it with a grain of salt. I think that there's if you haven't seen the CB Insights AI 100 from this year, it's a really great cohort. We lucked out to get included in that, but there's a lot of great firms in this area. Hugging Face is organizing it, definitely. I will definitely call out, Ben Lorca did a great interview with Andrew Burt recently about navigating the risks in this landscape, and definitely from an attorney's perspective who really understands what's going on in generative AI. Highly recommend that. And I think, otherwise, I'll just put up, we have some resources online, and thank you very much.